In your hand, a simple grain of sand. In your veins, a drop of blood. In both, atoms forged in the fiery hearts of stars that died billions of years before our Earth was born. We are, quite literally, made of stardust, cosmic wanderers fashioned from the remnants of ancient suns. The story of stars is our story, an epic tale of creation, transformation, and rebirth that spans the entirety of cosmic time. Across the vast expanse of our galaxy lie clouds of gas and dust, cosmic wombs pregnant with possibility. These nebulae, some spanning hundreds of light years, appear serene from a distance, their delicate wisps and tendrils painted in ethereal blues and vibrant crimsons. But look closer, and this tranquility gives way to turbulence. Within these stellar nurseries, gravity works its patient magic. Over thousands of years, it gently pulls hydrogen and helium atoms together, creating ever denser pockets within the nebula. Each gravitational embrace draws more matter inward, a cosmic dance growing ever more frenzied as particles collide and temperatures rise. When the heart of this embryonic star reaches 10 million degrees Celsius, a miracle occurs. Hydrogen nuclei, once repelled by their positive charges, are forced so close together that they overcome their natural aversion. They fuse, releasing extraordinary energy in the process. Nuclear fusion, the same process that powers hydrogen bombs, ignites, and a star is born. The nebula surrounding this stellar infant is blown outward by stellar winds, sculpting the remaining gas and dust into fantastic shapes, pillars, globules, and arches of sublime beauty. Within a single nebula, hundreds or even thousands of stars may form, a stellar litter bound by gravity and shared origin. And so the first chapter of our stellar story begins not with a solitary birth, but with a family coming into being, siblings of gas and fire that will journey through the cosmos together. For stars, middle age is a time of remarkable stability. Our own sun, now 4.6 billion years old, has settled into this mature phase of stellar life, what astronomers call the main sequence. Here, a perfect balance exists between two titanic forces, gravity pulling inward and the pressure of nuclear fusion pushing outward. This cosmic tug-of-war creates a stellar equilibrium that can last for billions of years. But not all stars are created equal. Their mass, determined at birth, dictates their entire life story. The most massive stars burn hot and bright, their lavish expenditure of fuel ensuring a brief but spectacular existence. These stellar giants, blue supergiants like Rigel in the constellation Orion, may live only a few million wars before exhausting their hydrogen fuel. In contrast, the smallest stars, red dwarfs like Proxima Centauri, burn their hydrogen with miserly restraint. Their nuclear furnaces operate at lower temperatures, allowing them to shine for trillions of years, far longer than the current age of the universe itself. Our sun sits between these extremes, a middle-class star of average brightness and moderate lifespan. Every second, it converts 600 million tons of hydrogen into helium, releasing energy that eventually reaches Earth as the sunlight that powers nearly all life on our planet. As we bask in this stellar radiance, we seldom consider that the light warming our skin began its journey from the sun's core, where it was born in fusion reactions, before spending thousands of years bouncing through the dense solar interior. What reaches us in 8 minutes has been thousands of years in the making, a reminder that even in stability, stars operate on timescales that humble human perception. All equilibrium, no matter how perfect, eventually comes to an end. For stars, the first sign of aging comes when hydrogen in the core grows scarce. As fusion slows in the stellar heart, gravity momentarily gains the upper hand, compressing the core and raising its temperature. This heat ignites hydrogen fusion in the surrounding shell, causing the star's outer layers to expand dramatically. Our Sun, once its hydrogen core is depleted, will swell to hundreds of times its current size, engulfing Mercury and Venus and perhaps even Earth. Its surface will cool as it expands, shifting from yellow-white to a deep, smoldering red. This red giant phase marks the beginning of a star's twilight years, a period of remarkable transformation. In stars like our Sun, the compressed core eventually becomes hot enough to fuse helium into carbon and oxygen. This new source of energy temporarily stabilizes the aging star, but when helium too is exhausted, the star enters its final act. Unable to generate the pressure needed to counteract gravity, the outer layers of the star begin to pulsate, shedding shells of gas that drift outward into space. These expanding shells, illuminated by the hot stellar remnant at their center, create some of the most exquisite structures in the cosmos, planetary nebulae. The Ring Nebula, the Butterfly Nebula, the Cat's Eye Nebula, each is a stellar death mask of extraordinary beauty, a luminous farewell from a star that once shone steadily for billions of years. At their centers lie the exposed cores of the former stars, white dwarfs, dense spheres of carbon and oxygen, roughly the size of Earth, but containing the mass of a star. These stellar embers will cool slowly over trillions of years, their light gradually fading like memories of a life well lived. For the most massive stars in our universe, death comes not as a gentle fading, but as a cataclysm of almost unimaginable violence. When a star at least 8 times more massive than our Sun exhausts its nuclear fuel, its core collapses within seconds. The star's outer layers, suddenly unsupported, plummet inward at 1/4 of the speed of light. When these falling layers hit the collapsed core, now compressed to the density of an atomic nucleus, they rebound with extraordinary force. The star tears itself apart in a supernova explosion, briefly outshining entire galaxies of billions of stars. The energy released in these few seconds is so vast that it forges elements heavier than iron, gold, silver, uranium, elements that cannot be created in the normal fusion processes of stellar life. These newly minted atoms are hurled outward at millions of miles per hour, enriching the interstellar medium with the building blocks of planets and, eventually, life. What remains after this cosmic conflagration depends on the original star's mass. For some, a neutron star forms, an object so dense that a teaspoonful would weigh 1 billion tons on Earth. These stellar corpses spin with extraordinary precision, some rotating hundreds of times each second, sweeping beams of radiation across space like cosmic lighthouses. For the most massive stars, not even the pressure of neutrons can halt the collapse. Space and time themselves surrender to the inexorable pull of gravity, and a black hole is born, an object from which not even light can escape. At its center lies a singularity, a point where our current understanding of physics breaks down entirely. These stellar remnants, white dwarfs, neutron stars, and black holes, represent the final chapters in the lives of individual stars. But in cosmic terms, they are merely commas in an ongoing narrative, pauses before the story continues in new and unexpected ways. The atoms in your left hand may come from a different star than those in your right. The iron in your blood and the calcium in your bones were forged in stellar furnaces that exploded long before our solar system formed. We are, in the most literal sense, recycled stardust. When stars die, they seed the cosmos with the elements they've created during their lifetimes. These stellar ashes drift through space, sometimes for millions of years, before gravity once again draws them into new nebulae. Here, enriched with the products of previous stellar generations, they form new stars and planetary systems. Our own solar system represents at least the third generation of this cosmic recycling. The heavy elements that make up Earth and its sister planets could only have been created in the deaths of ancient stars. Without these stellar ancestors, these long-extinguished suns, the chemical complexity needed for planets and life would not exist. Even now, this process continues throughout our galaxy. In the constellation Orion, new stars are forming from the remains of those that died millions of years ago. In the Crab Nebula, the debris from a supernova observed by Chinese astronomers in 1054 CE expands outward, its material destined to be incorporated into future worlds. This is the true immortality of stars, not as eternal, unchanging objects, but as participants in an endless cycle of transformation. Their substance never truly dies, but is continually reborn in new celestial configurations, and, on at least one world that we know of, in the bodies of creatures capable of looking up at the night sky and wondering about their origins. We began this journey with a simple truth. We are made of stardust. But perhaps the more profound realization is that we are not merely the ash of stellar fires, but their continuation. The same fundamental forces that ignite stars operate within us. The same elements forged in their hearts flow through our veins. The same cosmic story unfolds in our DNA. When you next look up at the stars, remember that you are not merely gazing at distant suns, you are looking at your ancestors. And in the fullness of time, every atom in your body will return to the cosmic cycle, perhaps to form new stars, new planets, new life. We are not separate from the cosmos. We are the universe contemplating itself, stardust reflecting on its own remarkable journey.